So good evening, everyone. Welcome to today's talk and thanks for logging in. And also big thank you to ACS India team for organizing the talk today. And in fact, not just for inviting me as a speaker, but also as a audience member for a few of their other talks. I've got to learn a few things while we stay locked up. So hopefully you're all doing well and you're all safe. What I want to talk about today is 3D printing for biomedical applications. We are a biomaterials lab. We do a little bit of 3D printing. In fact, increasingly we do more of it. But actually, I'm not going to talk about what we do. I thought this would be a good time to see what people around the world in this field are doing, and hopefully get sort of an overview of what's going on, where the future is, what one could do with these kind of technologies. So we'll start with what is 3D printing, or also known as additive manufacturing. So what you can see here in these slides, in this figure, is that there are basically two kinds of manufacturing techniques, or two classes of manufacturing techniques that have been around for a long time. There's formative manufacturing and there's subtractive manufacturing. In formative, you basically have some sort of a mold or a cavity in which you pour liquid material, and then that solidifies and you get the object of your interest. In subtractive, which is basically like machining, you would machine a block of material and you get the object of desired shape and size. Now, additive, although it's been around now for a while, it's actually getting more traction in recent years. It deals with making a material or making a part by building up the part layer by layer and forming a 3D object. So the question is, are additive manufacturing and 3D printing, are they interchangeable terms? Are they the same? Are they different? Well, they're actually quite similar, not identical though, if you go exactly by technical terminologies. So AS Team International defines additive manufacturing as a process of joining materials to make objects from 3D model data, usually layer upon layer, as opposed to subtractive manufacturing technologies. 3D printing is defined as the fabrication of objects through the deposition of a material using a print head, nozzle, or another printer technology. So the subtle difference is that in 3D printing, you have to have some sort of a nozzle or print head where the material gets deposited. In additive, it's a broader term where some of the 3D printing techniques don't necessarily, or I should say, okay, let me put this way. Some of the additive manufacturing techniques don't use a nozzle, and therefore those would not really be 3D printing. Nevertheless, the people in the field do use these two terms interchangeably, and we are going to do the same for the discussion today. So when would you use additive manufacturing? Should we get rid of formative and subtractive manufacturing? Well, if you look at this plot here, the answer would be no. If you want to make parts, thousands, millions of a part of a given shape and size, then you would, you're still better off doing formative manufacturing. If you're doing parts which are relatively simple in geometry and at fairly large volumes, even if it's not thousands or millions, you would still be better off with subtractive or machining. Where additive really plays an important role or is attracting a lot of attention is where you need to make complex designs, and particularly at low volumes. So the advantage really is the ability to prepare complex shapes and porous structures. And there are additional advantages like the so-called low buy-to-fly ratio. What it means really is if you have a certain amount of material from which you're going to make your object, in machining you actually end up removing a lot of the material and it goes for waste. And that can add to your cost, which you can reduce in additive. And if your material is expensive, you may actually benefit by using additive manufacturing. Then there is, of course, the benefit of saving direct costs, because you'll end up reducing a lot of tooling and assembly line and assembly time that is involved in conventional manufacturing. So what we'll do is we'll look at various categories of materials that are used for additive or as biomaterials, and how they are processed by additive manufacturing and how people are trying to explore their use in biomedical applications. I'll start with metals, and this is a picture taken from a relatively recent paper. And what they've done is listed several of these biomedical implants that are prepared using various kinds of metals. starting from cranial implants to knee prosthesis, hip joints, and there is spinal and dental implants and so on. And in fact, most of these shown here are indeed prepared by 3D printing. And as you may know that there are a very narrow range of materials that are used for clinical applications as far as metals are concerned. So there's a Ti6, Ti6 aluminum, 4 vanadium. There is 316 cell grade of stainless steel. There's cobalt chrome based alloys, and nitinol, which is nickel titanium alloy, and a few devices that are made out of titanium, made out of tantalum. And more recently, there is a lot of interest in trying to use these resorbable or degradable devices or materials as biomedical alloys, such as zinc, calcium, and magnesium, but these are mostly still in the research state and haven't quite made it to the clinical translation stage. So, why would you want to do additive manufacturing, let's say, of metallic implants, right? So there are several advantages, and I've listed a few here. One is you can actually make or print personalized devices, which means basically medical devices that have the best anatomical match to a particular patient. So you can see in this figure here that if one needed a knee implant, and if you did mass manufacturing, there is a probability that for many patients, the devices might be a little too big or too small for their particular anatomical defect site. So what one could do then is try and make devices that fit exactly to meet the patient's needs. So in principle, what you would have to do is to image that patient's defect site, recreate that in the software, make a design of the best device in that software, and then print it. And you'd be surprised that actually there's been quite a bit of progress in this field, and there are companies which do offer this kind of technology now for clinical use. So this is one such example, these are titanium 3D printed implants for facial reconstruction. And these are, again, personalized devices for best anatomical match. The other advantage of metal additive manufacturing is basically the ability to make complex geometries. It could be external shapes and intricate internal architecture. So here is one example where these are parts of a knee implant, and you can see here various kinds of porosities and surface architecture that's been prepared. The idea is to have better tissue ingrowth. Here's another example where they prepared a metallic implant where they're trying to mimic the architecture of bone. The idea being that with this kind of porosity, you will be able to mimic the mechanical properties of the bone tissue, and therefore it should integrate better with the body. The other application advantage of this kind of an application for metallic implants is to reduce the stiffness of these implants. This is a common problem with metallic implants, which is that the elastic modulus tends to be very high compared to that of bone tissue. And so consequently, there is stress shielding, and that will hinder osseointegration of the device with the surrounding tissue. So the idea here is if you made porous structures, that will help to reduce the elastic modulus, and that gets you a better match with the bone, and therefore you get better osseointegration. So some of these applications or advantages would also work for the case of ceramics and polymers, but we are looking here particularly for metallic implants. The question next that we should ask is, how do you go about making these kind of parts? So there are various techniques, and I won't be able to cover everything, and I don't want to necessarily just keep on listing the different techniques. Try and give you an idea of what these techniques do or what the strategy is, and then you can see what the differences are, and a lot of other details or specific I should say details of a new technique that comes out would probably be an alteration of some of these techniques. So the way to classify them could be based on how the material is fed. So based on the feedstock, you could have powder beds, or you can have a nozzle through which you feed the powder, or you can have a wire that is used to feed the material. The other way to classify these techniques is how do you melt the metal and form the 3D part. So you could use a laser, you could use an electron beam, or you can use plasma. So the most popular technique in metal 3D printing is this technique called selective laser melting. There are various other names that I've listed here, which are also used to refer to this technique. The idea is sort of captured in this schematic shown here. Basically, there are two chambers, and this orange really represents a bed of powder of that particular alloy that you're interested in printing. So the way it would start is there are two chambers, the build platform, and this can move up and down along the piston. And then there's a powder dispenser piston, which can also move up and down. So what would happen in the beginning is this platform would be, the build platform would be at the top, and this powder dispenser would be way below. And then when it starts, the powder dispenser platform would move up a little bit. The recoater blade would push a very thin layer of powder on top of this build platform, and you would have lasers to raster on this bed of powder, that thin layer, and then wherever the laser moves, it locally melts these powder particles or the metal powder, and then they would fuse and they would essentially form a continuous piece of metal. Wherever it won't come in contact with the powder, that would stay as powder, right? And so then in the next step, this build platform moves down by a small height, and this powder dispenser platform moves up again a little bit. You recoat it with another layer, and you keep repeating this, and that way you keep building it up layer by layer. When you try to do this kind of process, there are lots of parameters that one can play with. There are parameters related to the laser, like its power, the spot size, its duration, frequency, and so on. The choice of powder itself is important. For a given composition, you have to think about its size and the size distribution, the shape. You want it to be spherical, not some sort of irregular or elongated shape. The density matters, so does the thickness of the layer that you're depositing every time. And there is the scanning speed, the spacing, the pattern, the temperature at which you hold the bed, the build plate, and so on. A lot of these parameters will make a difference. And in fact, there can be up to 180 different variables or processing parameters that can make a difference in terms of what the printed part would look like or how it would behave. These techniques are relatively new, or there's a lot of optimization that's still being done. But among these various techniques, SLM is probably the most matured metal printing technique. And there are several suppliers now that do supply SLM printers, and the build size or the platform size can vary quite a bit. Also, what is quite useful from a biomedical standpoint is most of these conventional alloys, like the titanium alloy, stainless steel, cobalt chrome, you can actually buy the powder from commercial sources, which makes it quite convenient to be able to use metal 3D printing to make biomedical devices. But there are a lot of other challenges and difficulties with this. Number one is the cost of the equipment. These printers will cost tens of lakhs, often a couple of crores, and also the operations being, you can see how many parameters are there, which means then that maintaining the equipment and having technically qualified staff to run the equipment, all of this is a costly affair. Then the handling the powder and even getting the powder in the first place, especially if you're thinking of a new alloy, for example, would be a challenge. Then when you print, once you've taken out the printed object and the rest of the powder, you don't want to throw that away, you want to reuse it, but then that comes with its own difficulties because it can get contaminated. So handling, reusing is a challenge. And the printing speed is not all that great with SLM. The surface finish that you get is quite rough. If you don't do your printing right, you're going to run into all kinds of defects shown as examples here in the figure. So there's porosity, there's gas filled voids, then the materials can delaminate, and they're all, and more often than not, for the printed metals, these parts tend to be very brittle, and therefore they need a lot of post-processing in terms of improving the surface finish, the mechanical properties, and so on through heat treatment and other surface engineering techniques. There are other variations of this. So instead of using a laser to melt your particles, you can actually use an electron beam. So here, this is then that would get you the technique called electron beam melting. So here, the temperature of the bed is held much higher. So the residual stresses on the printed part is lower, and therefore it's quite ideal for printing brittle materials. The cost is much higher. So you're probably talking about now 8-10 crores for that equipment, and also there's only one supplier, so you don't get too much variety in terms of buying these equipment. Then you could build one, but that also is not easy. This is even slower than printing with SLM. Many more parameters, so it's more complicated, and because there's only one supplier, not many people work on this technology, you won't get too many optimized parameters for various kinds of alloys. Nevertheless, you will find there are quite a few studies where people have tried, at least on a lab scale, and in many cases, even in human trials, tried to put these printed implants. And what they've done is made various shapes and sizes of these implants. In this particular example, these are cranial implants, and they have shown that they can be implanted without major side effects, and more research is going on in this field. In contrast to using a powder bed, one can use another class of techniques which are known as directed energy deposition, or DED techniques. So here the idea is to fuse the material by melting using a focused energy beam. That beam could be an electron beam, it could be a laser, in some cases even a plasma. But the difference is, unlike a powder bed, here you feed the material along with the energy source. So on the left is if you use a powder source, and you can see there's a laser beam, and also there is powder that is being fed from the side. Or you could use a wire DED technique, where there is a wire that's being used to supply the material. So advantages, of course, being that it's much faster now than the powder bed techniques. And also you can build it on any existing substrate, which means that you could, if there is already a part that was prepared by some method, whether it's additive or some other technique, you can use it to heal or repair those materials. You can deposit coatings on them. And also you can make these compositionally graded materials very easily by changing the feed material that's going into the device. And these are again some examples of attempts at trying to make 3D printed parts using these DED techniques that people have tried. And these are some hip stems that have been printed using various DED techniques. So we'll switch from metals to ceramics. So here again, when you talk about ceramics, you're mostly talking about orthopedic and dental applications. And this is a nice image from the American Ceramic Society website, where they've printed or shown a variety of devices that have been prepared by printing ceramics. And here again, you can classify the technologies for printing basically based on feedstock. So it could be powder or slurry. So with powder technology, of course, you can use that SLM-based technology where you use a laser to sinter the powder, or you can use binder jet, and we'll talk about that in a minute. And then there are the slurry-based techniques. Aside from SLM, most of these other techniques, what they will get you is a weakly printed or a weakly held part that is produced as a result of printing, which we would call a green part. Now that would have to be kept in a furnace as sort of a post-printing step, and then that would help in sintering of the particles better and getting a more mechanically robust part. And that would be what we would call a brown part. So moving to binder jet printing, here the idea is that you have a print head which will deposit binder. So you have a powder bed. This time this is the bed of ceramic powder. So you have inkjet print head here, which is depositing some sort of a liquid, typically with functional groups that they can at least weakly hold the ceramic particles together. So here again, this is being done layer by layer. So places where this binder is deposited, you land up getting some sort of an adhesion between the particles. Elsewhere you don't. So after it's printed, you can take out that that part, and that would get you that green part, or the green state of that printed part, that you would put in a furnace for sintering, and that gets you the final brown state object. So here with this technique, which has been around for a while, you can work with a variety of ceramics, but you will run into problems with shrinkages and high porosity, because as the binder is sort of burnt off essentially during sintering, you will create a lot of porosity, and therefore you don't get great resolution, and the surface finish is very rough, which may not be all that bad, because there are examples or applications, in particularly for bone related implants, where you would want a rough surface. So this is an example where they printed a device here purely out of hydroxyapatite, and this is the device design, this is the printed part, and they actually implanted them, I think, in rats. And the idea of having these holes and even this rough surface was to have vascularization of the bone that is being formed as this material gets resorbed and integrated with the body. So this is actually used quite a bit for biomedical applications. The other technology is to use inkjet printing. So here you, instead of using the powder bed, you have a slurry. So the powders are dispersed or in some sort of a liquid, which could be a solvent, it could be maybe a small molecule, which like an oil perhaps, which will help you get some sort of liquid that is deposited in various locations, and typically in the form of drops, and this is done through a nozzle. Now this actuation can be done in one of two ways. One is by using a heating element. So there's an instantaneous heating which creates a vapor bubble, and that pushes a drop of liquid out. The other way to do that is mechanical actuation, where you use a piezoelectric actuator and you mechanically press it, or as it expands, it pushes a drop out. So this is also a fairly low cost, simple technique. It's very useful for making small size parts, but it's a bit of a trick or a challenge to be able to make the right formulations. What kind of a liquid would you use? How much particle would you add in? Then, post-processing, you don't want too much porosity, otherwise the thing will fall apart. So these things have to be optimized. Another way to do 3D printing with ceramics is a technique called direct ink writing. You can think of it as a much thicker slurry now, almost like a paste. So here you're doing layer by layer deposition of colloidal or polymer-based inks. I can probably draw an analogy to a toothpaste tube. So if you could just squeeze it, you will have that paste coming out. And so depending on then the kind of design you have, you could try to make a solid device, solid part or a printed structure. And these are also very low cost. They're a fast technique. They're good at actually printing porous scaffolds, not so much dense parts. And also the surface finish tends to be quite rough. And this is again something that's been around for a while. And you'll find various examples where people have tried using this technique to print ceramic scaffolds. And this is an example where they printed, again, hydroxyapatite scaffolds for mandible repair. So you can see here, this is the defect site that they want to heal. So they get the design out of that by scanning the patient's mandible, and then they can print that scaffold. They optimize the size and various other parameters of the scaffold, and they've actually implanted it back into a person. So that is about ceramics, and I'm going to try and cover a little about polymers before we run out of time. So polymers, as you probably know, are very widely used in a wide variety of biomedical applications. There are various ways to classify them. From an applications perspective in a biomedical setting, I would say you could think of two classes. There are the non-degradable ones, and then the degradable polymers. So the non-degradable polymers would get used in implants, and then there are the degradable polymers that are used in a variety of other applications like tissue engineering, in drug delivery, and a host of other applications. So here again, in terms of applications of 3D printed parts, one would be what we've already discussed in the context of metals and ceramics, which is you make personalized or patient-specific devices. So here you scan the patient's defect site, you recreate the model, you print it with a 3D printer, and then you can implant this back into a person. But another thing that is actually taken off in a big way, because it probably doesn't require all these regulatory clearances and so on, is to prepare these surgical mimics. So here the idea is that if you're a surgeon and you're going in to do a very difficult surgery, it would be nice if you had a model in which you could practice before the actual surgery is done. So what they do these days is, for some of these surgeries, they will get the patient's organ or tissue scanned, and then they will use a 3D printer to print a soft polymer, because typically these are soft tissues that they want to mimic. And then the surgeons get to practice on these tissue mimics, and then on the day of surgery they're better prepared to do the surgery, compared to coming in blind without knowing what to expect. The other thing that you could do with 3D printing of polymers is to mix them with drugs and have personalized drugs, essentially, or personalized medicine. So if you knew what the diagnosis is of a particular patient, and therefore what kind of drug regimen you would want for them, you can print it in such a manner that you get particular profiles of drug release, and that would hopefully get better outcomes in terms of healing and treatments, right? Okay, so then how do you go about doing 3D printing of polymers? So the most popular technique is fused filament fabrication, also known as fused deposition modeling. So here, and I should point out, this is probably the cheapest 3D printing technique. These printers are available even online for maybe 10,000-20,000 rupees. Of course, they are not necessarily the best ones. The ones that are very versatile would probably cost more, but still these are much more affordable than other technologies. So the idea here is that you have a material feeder, which the material is fed in terms of a filament or a wire of this plastic or the thermoplastic. And the idea is that this is wound onto a spool, and then the filament is pulled through these rollers, and they go into an extruder. The extruder has heating elements so that the polymer will melt and it is extruded out. The head can move in X and Y, and your building platform can move in the Z direction, and that way you can build up your printed part in 3D. And you won't get great resolution. Also, you can only do simple geometries. Nevertheless, you can do 3D printing, and you can even do it at home if you like with some of these simple FDM or FFF printers. For biomedical applications, since you are using high temperatures to melt the polymer, you can't incorporate living cells or labile biomolecules at time of printing. Once you printed the scaffold, you can add them on top of the printed part. So this is one example where people have tried to use this kind of technology to make anti-infective dialysis catheter. So they've taken a polyurethane and they've added an antibiotic. In fact, there are some other additives they've added so that the drug is stable and also you get sustained release. So they've made a few designs. They've used the 3D printing and they've printed these parts. And what they show here is that the drugs exhibit sort of a controlled release from these devices, such that if bacteria were to adhere to it, it would be resisted by the release of drugs, and therefore you can minimize infections during dialysis by using these kind of catheters. Then there are a whole bunch of other techniques for polymers. There is selective laser sintering. So here, much like what we've talked about for metals and ceramics for SLM, here you're again using a powder bed, but now you don't use very high temperatures or very high laser power. So you don't really melt the particle or of your polymer. You actually just soften it so that it just sinters, and instead of melting and solidifying all over again. But it's the same sort of idea, and then you can use it for making all kinds of devices and scaffolds. This is direct ink writing. Here again, like I said, for the case of ceramics, Here you would take a polymer, you will dissolve it in an organic solvent. Typically, you make a thick paste that you can just extrude out and print it layer by layer. In this particular study, what they did is to take polycaprolactone, which is a biodegradable polymer, and they have played around with different solvents, and the concentration and the choice of solvents, what that does is it gives you various kinds of micro and nano topography on the printed scaffold. So if you take one of these printed struts and you zoom into that, you see various kinds of structures. And then on top of that, if you add in stem cells, what you find is their function, the growth, their function, their differentiation gets altered as you change the micro and nano structures on these printed scaffolds. Inkjet printing is also very popular with printing of 3D printing of polymers. So here there are two variations of it. You could do it with a powder. So this is again a powder bed, and you essentially add a binder solution drop by drop onto the layer with your inkjet technology. Or in this other technique where you're using a liquid, you have a photosensitive resin. So you have a reservoir and there is a nozzle head where this is being extruded. And as each layer is getting extruded, these tend to be typically your photosensitive resins. So you can turn on UV light so that each layer gets cured, and then before you print the next layer, and that way you can build up a 3D printed part. The last category of 3D printing of polymers would essentially be the vat-based 3D printing techniques. Most popular of that would be the stereolithography technique. Here, again, you're really talking about light-sensitive polymers. So here, the idea is that you would take a vat or a bath of this kind of a light-sensitive or photosensitive polymer, and you would use a laser to essentially raster layer by layer. Here, you're not extruding any liquid or any polymer out. What you're doing is just rastering the laser in such a way that wherever the laser spot is, that is where the polymerization happens, and you get the solid polymer to form there. The rest of it stays liquid. So once you're done printing, you can pull this out, wash off the uncured resin, and you get your 3D printed part. So this really gives you the best resolution and accuracy, also gets you a good surface finish. And there are quite a few attempts in trying to use this to make 3D printed parts for biomedical applications. So there's a biodegradable polymer called polypropylene fumarate. So here you can see stereolithography has been used to print a scaffold of this PPF polymer. There are other variations of this vat-based printing. So you can use what is called digital light processing. So instead of using a laser where you're moving from one spot to another and that slows you down, you can just do it in a flash in a layer by using this digital micro mirror device. So here, instead of doing it point by point, it is like plane by plane, which means that you get higher throughput printing and you can actually build much larger sizes. There's also something called two-photon polymerization printing. So here you're using a femtosecond laser. So the idea is that when there are two photons that come together, and this is typically in a very small volume, the photopolymerization will happen. And as a result of this, and because it's sort of a non-linear event, what happens is this is restricted to a very small volume, and therefore you can get resolutions down to about 100 nanometers, which would be very difficult to achieve with any other kind of 3D printing technology that's currently available. In fact, you could vary the stereolithography technique to adapt it for ceramics. So when if I go back here and talk about the stereolithography in this vat of this photocurable polymer, if I disperse ceramic micro and nanoparticles, then I can cure it, and layer by layer, after that ceramic polymer mixture has been printed, I can then sinter it, get rid of the polymer, and I can get ceramic structures or parts to be formed with that technique. And then you will get, though, very large shrinkages. And one of the major problems you will encounter is that the solution will now no more be transparent. It will have the white particles of ceramic, and therefore they will scatter the light, and sometimes the part doesn't look all that great. But nevertheless, people have tried to do that kind of a strategy to print these, in this case, dental implants that have been prepared by stereolithography for using ceramic materials. Now, there is a subset of 3D printing using polymers, which would essentially be what I would call bioprinting. So here the idea is that you want to be able to print along with living cells. Everything we've talked about so far is you print your part and then you add your living cells. Here you work with materials that are compatible with living cells, or they can polymerize and entrap the cells. And this class of polymers would be all your hydrogels, which are essentially a water-swollen 3D networks of hydrophilic polymers. So if you're not aware of how hydrogels work, I just put a slide here or a picture here. So you can see there are these precursors which typically have some sort of a group at the ends that can react because of some sort of a stimulus. That could be light, that could be some chemical reaction, and you mix cells with them. And then when you give that sort of a stimulus, let's say it's a photosensitive polymer, you turn on the particular UV light, these chains will react and they will form a network, and they will, and while that happens, the cells will get entrapped. And the idea is that you use degradable polymers so that when the cells secrete their own ECM, they form the tissue, the hydrogels will degrade. Now, this has been around for a while, and people have started adopting 3D, hydrogels to, along with 3D printing techniques to print live cells. So the techniques are pretty much what we've discussed. So you can have inkjet bioprinting. So here, if you take the hydrogel along with your cells, you can have actuation, and drop by drop, your cells along with the polymer would get deposited on the substrate. You can have extrusion-based printing. So basically, you have a nozzle in which you fill in this hydrogel with the cells, and you can push them out using a pneumatic or screw-based mechanical system. You can have stereolithography. So now you have not only your photosensitive polymers, but you have cells dispersed in them. So if you turn on the light, the layer by layer, the material will get polymerized, and that will entrap the cells. And there's also laser-assisted bioprinting, which is sort of like inkjet bioprinting, but it's contactless. So there's like a glass slide and a layer of this bio ink with the cells along with the bio ink. And when you shine the laser at a particular spot, this polymer will drop from there, and then that can be deposited at various positions. It's sort of similar to inkjet, except you don't make any physical contact, and there is no nozzle in this case. And each of these techniques would come with its own pros and cons. By inkjet, you get very good resolution. So, there's the same also with stereolithography. With extrusion bioprinting, it's not so great, but that's probably the most established bioprinting technique that's used around the world. In terms of the speed, you get very high printing or fast printing with inkjet and stereolithography, and slowest with extrusion. In terms of cost, here again, depending on how versatile your equipment is, it can vary quite a bit. Although if you were to get one of these commercial printers, I would say the most choices that you would have would be with your extrusion-based bioprinters. And so what do you do with a bioprinted tissue or this tissue-like construct? Well, one, of course, is once you've printed your construct, you could use it for tissue regeneration, which we've already talked about. The other thing you could do is not necessarily look at implanting it in the body, but mimic what's in the body on sort of the lab scale, right? So here, and that is what we call in vitro models. So I picked a paper here, where they've tried to look at how breast cancer metastasis happens to bone tissue. So what they did was to take gelatin methacrylate, which is basically gelatin with acrylate groups at the ends, and this would make it a photosensitive polymer. And you mix it with cells. In this particular case, these are mesenchymal stem cells that turn into bone-like cells. And they use stereolithography to prepare these scaffolds. The first thing that they did was to study the differentiation of these mesenchymal stem cells into osteogenic lineage in these scaffolds. And after that had been established, what they did was to set up a co-culture where they brought in these breast cancer cells and put them on these scaffolds. The idea is that if in the body you can think of breast cancer cells moving from the breast and colonizing a piece of bone, if you wanted to try to understand the mechanism or you wanted to test drugs, these would be very useful models that are much better than, say, trying to do a co-culture in a petri dish. I'm nearing the end of my presentation, but I can't not talk about an emerging topic, which is 4D printing. And here it utilizes all the technologies of 3D printing, except the principle is that the 3D printed part can transform into another stable structure after it's been printed, provided you give it an external cue. And that cue could be the temperature change, it could be pH, it could be light, magnetic field, and so on. Most of these are based on using shape memory materials. And you can imagine here that if instead of printing a cube like this, if we had printed a sheet and then we give it some sort of trigger such that these flaps would fold and they'd form a box, then that would be really what we would call a 4D printed object, or a 3D printed object that exhibits 4D printed behavior. So here is an example, not necessarily biomedical, but what they've done here is printed multi-material grippers. So, and these are shape memory polymers. And what they've shown here is and they've used a variety of polymers to make this particular part. And by heating and cooling, what they can do is make it go from one state, a closed state, to an open state. And their idea is that one can think of these as soft robotics or grippers, where you can pick up small objects and move them around, and one could actually prepare them using 3D printing. There are not many examples for biomedical applications. There is one example where it's a report that came out a few years ago where they've tried to print what they call personalized medical device. In this particular case, it's an external airway splint. And what they've done is they've printed this particular device, if you can see here in the figure. And this is made out of polycaprolactone. It's not really truly a 4D because it's not like changing from one state to another. But what it does though is, because of the device design, it can accommodate the growth of this airway. And especially in infants, if they have a collapsed airway and they would like to keep it open, but then the infant will grow over time. So they would want a device that can adapt to the growth of that patient. So what they have shown here in this particular figure here is that there is an airway that's collapsed, and they put this device around it and they suture it. And then what it can do is, as the child grows and this airway becomes bigger, because of its particular design, this device can open up more and more. And that helps to maintain the airway in an open state, but also accommodate the growth of the patient. So this is actually a small clinical study they've done with this. So the clinical condition is that there's excessive collapse of that airway during respiration that leads to this life-threatening cardiopulmonary arrest. And they've taken 3 very young patients. Initially, you can see the airways are all collapsed. They implant these devices and they do a follow-up for several years. Immediately after implantation, they see there is significant improvement in their physiological parameters. And also long-term, up to 3 years, they find that the material has degraded, the device is gone, but now the airway stays open. And so this condition is essentially healed in these kind of patients. I don't know if you've noticed news in recent times. Of course, we are all, aware of COVID-19, but people are using 3D printing to address some of these needs that have come up. So this is a story from Italy, where with ventilators, they need a specialized heart valve for these respirators. And what they've done is they've taken the design, they fed it into a 3D printing a printer, and then they have printed these valves that can be quickly deployed. So it doesn't require a lot of tooling and assembly lines, and therefore it becomes quite convenient. And this is a story from Bangalore, where there's a company, and they're not the only ones. A lot of people around the world were trying to use 3D printing to make face shields. In fact, when you talk about COVID-19 and you look at all the news that's coming in, there's a lot of hope that there will be drugs and maybe even a vaccine. And so you'd be surprised that you could actually use 3D printing to, change the efficacy of vaccine delivery. So this is a very recent study from this journal Biomacromolecules. And what they've done here is, as proof of principle, they've tried to look at 3D printed structures where these are nanoparticles that contain the antigen. And so what they've done is they've taken these proteins, this is bovine serum albumin with a photosensitive molecule, and they have used multi-photon polymerization to print these nanoparticles. And they can actually get a variety of shapes and sizes. These are microns to submicrons sizes and features on these particles. And what they found is, of course, with the change in the particle shape and size, they get different cellular response. But also, if they change the length of these particles, the aspect ratio, when they give these particles to macrophages, there is a difference in the response. The TNF alpha is measured in this particular figure, did seem to get altered if you increase the aspect ratio of these nanoparticles. So maybe one day when we have, say, vaccines for COVID or other kinds of viruses that we are dealing with, one could perhaps use 3D printing to improve their efficacy. So with that, I'll end my presentation. So hopefully I've managed to give you an overview. I'm sure no matter which market report you look at, they'll tell you that the future is very promising for 3D printing. There is already a market worth billions, but in another few years, you're talking about 5 to 10 times increase in the market size. There are products of various kinds, starting from orthopedic implants, dental implants, tissue mimics, and so on. For various kinds of materials, there is scope for coming up with new processes, of course, overcoming the challenges of the existing methods. So there are a lot of opportunities for everyone to utilize 3D printing for their work. Before I end, I must thank ACS team once again. And also, I didn't talk about what we do in our group. We do a little bit of 3D printing for a variety of applications, and all of that work is supported by a lot of funding agencies in India. Thanks once again, and hopefully everybody is excited about 3D printing, and the moment lockdown ends, everybody will start doing 3D printing.